Welcome to the first lecture on trigonometric functions. We will start with discussing a little bit of background which you would have already studied in your 10th standard. It is basically a Greek word which is composed of trigono and metron. So, trigono means triangle, metron means measure. So, it is essentially the study of measuring the sides of triangles and also finding the relation between the angles and sides of triangles. For example, let us take this right angle triangle here ABC. So, this is 90 degrees, let this angle be theta. You would have studied in your 10th standard that where you would have defined your trigonometric ratios, for example, cos theta, sin theta and tangent of theta. So, for this angle theta, we say this side AB as the adjacent side and this side AC, which is opposite to the right angle in the right angle triangle, is called the hypotenuse, and this side for this angle theta, this side AB is called the adjacent side, and the side opposite to this angle theta will obviously be called the opposite side. And if you recall, cosine of theta, which you write as cos theta. So, cos is actually a sort of short form for cosine. So, it is actually written as cosine, and cos is the short form for it. So, cos theta, you have already read this, that it is actually equal to the length of the adjacent side, which is length of the segment AB, upon the length of the hypotenuse, which is length of AC. Sin theta, again sin is a short form for sine, sine. Sin theta is equal to the length of the opposite side, which in this case is the line segment BC, divided by the length of the hypotenuse, which is AC. And then finally, tan theta, which is the tangent of this angle theta, is equal to the length of the opposite side, which is BC, upon the length of the adjacent side. So, this is already what has been studied by you. Just a recap. These trigonometric ratios have been used by you to solve various problems, so one of them being problems related to height and distances. For example, this particular problem here, where you have a tall building here whose height is unknown to you. Let us say that the height is h meters, and when you stand up here at this point A and look at the top of the building, the elevation angle that you measure with respect to the ground AB is 30 degrees. When you move towards the building to another point C by 10 meters, so this distance AC is 10 meters, and again look up to the top of the building, the elevation obviously increases to let us say 60 degrees, and then you are of course asked to find the height or estimate the height of the building based on this measurement of these elevation angles. So, the way you do it is, so let h denote the height here, let the distance BC be equal to let us say s meters, and then you use the tangent formula. So, if you use the tangent formula for this angle which is 30 degrees, what you get is tan of 30 degree is equal to h upon s plus 10, because h is for this 30 degree angle, h is the opposite side and s plus 10 here is the adjacent, and of course, you know that tan 30 is equal to 1 upon root 3. And then you look at the other triangle CDB, this triangle, and you again write the tangent of the angle, the 60 degree elevation angle, and using the same formula you get it to be equal to s divided by s. In this case, tan of 60 is equal to root 3. So, now you got two equations and two unknowns, you should be able to find both h and s. There is a little question here. So, in the previous page, when we were discussing this hypotenuse, opposite and adjacent side, the definition of which side is opposite is very clear, because it is the side which is to the opposite of this angle theta. So, for example, if I were to consider, let us say, the same right angle triangle again, but instead of considering this angle, if theta were to be the other angle, angle ACB, if this were to be theta, then the definition, well, the definition of hypotenuse would still remain the same, because hypotenuse is the side which is opposite to the right angle. So, this will still remain to be the hypotenuse, but the adjacent and opposite sides will now change. Now, this side BC will be, so this side BC will be the adjacent side, and this side AB will be the opposite side, because now this AB is the side which is actually opposite to this angle now, that being the reason. So, if you would have seen angles are something which you will encounter everywhere. So, a natural question which comes to mind is how to measure these angles. So, one common measure that we know is degrees. But before that, let us define what an angle is. Now, consider this ray OA. So, this is a ray, and let us say that we rotate this ray about this point O. So, this will keep this point O as fixed, and then we will sort of, so we will keep this point O fixed, and then we will move A like this. So, this fixed point will be called the vertex, and suppose we move it anti-clockwise, and let us say that this is, so this tip here moves from this, let us say, this point A to this new point B. So, this length and this length is the same, and we just rotate it like this. Okay. Now, this side OA is usually called the initial side of the angle. So, when you rotate it, so angle, this angle is nothing but the measure of how much rotation you do. It is a measure of how much rotation is performed when you go from this position to this position. So, this side OA is called the initial side of the angle, this side OB is called the terminal side. When the rotation is anti-clockwise, as in this example here, the angle is said to be positive, and if the rotation, so this is, let us say, for example, let me draw another one here. Now, instead of rotating this OA anti-clockwise, if we rotate it clockwise, so let us say we go from here to here. So, this is the initial side, this is the terminal side. So, we are rotating it now clockwise. So, in that case the convention usually is that this angle will be negative. Now, to measure angles, there are two popular measures of angles. One is called one is usually one way to measure it is in terms of degrees. The other way to measure it is in terms of radians. So, we will discuss degrees first, because that is something which you would have already studied. So, if we start with one complete revolution. So, again we consider this ray OA, and suppose we rotate it like this. So, we take it all the way and then we bring it back. So, one complete revolution. So, one complete revolution is said to be 360 degrees. Now, that there is no math behind why this is called 360, could have been called 450 or 800 or 720. The reasons, as we know now, are primarily historic. So, we will stick to 360, and then of course, so one complete revolution is 360 degrees, then of course, 1 degree will be equal to 1 by 360th part of a complete revolution. Okay. So, that is how 1 degree is defined. So, 1 degree is essentially the 1 by 360th part of a complete revolution. Now, let us again look at that ray OA. Now, if you see if one complete revolution is going to be called 360 degrees, then if we only do 1/4 of a revolution. So, for example, if we go from this OA, which is actually lying down horizontally, to let us say OB, which is standing upright, and if we look at this angle here, then if you see, if we rotate this OB again by another, so let us say that this angle is equal to theta. So, if we rotate this starting from OB, if we again rotate this ray in the anti-clockwise direction by another theta, then we should be exactly lying down again, right, but in the opposite direction compared to OA. So, it will look something like this. So, let us say C. So, this also has to be theta, and then another anti-clockwise turn starting from OC and again by theta should take us here. So, this is another theta, and then again another anti-clockwise turn by the same angle theta will take us back to where we started from originally, which is OA. But then what we see is that 4 times, because if you add all these angles, then 4 times theta is exactly equal to 1 complete revolution, which we have seen in the last page is should be equal to 360 degrees, and therefore, this angle theta is 1/4 of 360, which is 90 degrees. And that is why if you change from a lying down position to straight upright, the amount of rotation that this ray would have suffered is 90 degrees. In a similar manner, lot of other you can define all other angles like 180 degree. So, 180 degrees will be, if you go back to the last slide, if you start from OA and if you take two 90 degree rotations. So, for example, if you go from OA to OB, so that is taking a 90 degree rotation once, and then another 90 degree rotation from OB to OC, and what you see is that this OC is exactly lying exactly down and is exactly opposite to this OA. So, essentially this CA is a straight line. So, COA is a straight line and the angle of rotation is this 90 plus this 90, and that is 180 degrees. So, that is why we usually say that a straight line is 180 degrees. Another measure of angles is called the radian, and that might be new to some of you. So, the way it is defined is, let us look at the circle here whose center is at this point O and whose radius is 1 unit. So, this is a unit circle, okay. And then consider this ray OA. So, this is a radius OA, length is 1 unit. Now, when you suppose we start rotating it in the anti-clockwise direction and just focus on the amount of distance moved by this tip here. So, for example, if you move this OA slightly, then this ray would look something like this and the tip comes here. So, this is the distance travelled, right. Now, if you keep on increasing the rotation angle, the length of this arc will increase, right. So, if we keep on increasing up till a point, let us say, so we started with the tip was at point A, we move to a point B such that the length of this arc AB is also 1 unit, which is equal to the radius of this unit circle, right. So, when that happens, the angle of rotation then is said to be 1 radian. So, a natural question that arises in the mind of a student is, what if suppose I have a radius OC here and now I suppose rotate it from OC to OD by an angle of 2 radians, and how much is the length of this arc CD? Of course, it appears that definitely it will not be 1 unit, probably be more than 1 unit, but how much exactly? That is not very difficult to see, because this angle 2 radians is nothing but it consists of 2 successive repetitions of rotations, rotating the ray by 1 radian 2 times. So, suppose we initially start with the tip of the ray at this point A, and let us say that we first rotate it by 1 radian. So, you reach this point, let us say B, and as per the definition what we have seen is that because this angle of rotation is 1 radian, and obviously the length of this arc over here, this arc AB, this length starting from here till this point B is also 1 unit, but we are looking to find the length of the arc when the angle subtended at the center by that arc is 2 radians. So, what we do is we then move ahead from B and we rotate further by another 1 radian. So, we start like this and then we again rotate by 1 more radian. So, we finally reach, let us say, some point C over here. So, this might not be looking exactly as 1 radian, but let us assume so. So, when you reach this point C over here, starting from this point B to point C, if you look at this particular sector OBC, and if you look at the sector OAB, so which is this sector, they are exactly identical, and therefore, this length BC should also be equal to 1 unit, because again the angle of rotation starting from OB to OC, going from OB to OC is 1 radian. Therefore, this length of this arc BC should also be 1 radian, and then we of course get the answer, because if you now find out the answer to this question, where we were asking you to find out the length of this arc CD, which subtends an angle of 2 radians at the center of the circle. Here what we have is an arc AC. So, I am talking of this arc AC, where the angle subtended at the center is 1 radian plus 1 radian, that is 2 radians, and you see that the length of the arc is this 1 radian plus this 1 unit plus this 1 unit. So, it is a total of 1 unit plus 1 unit is 2 units, and therefore, if the angle subtended by any arc at the center is 2 radians, then the length of that arc will be 2 units, right. So, it appears that if you double the angle of rotation, then the length of the corresponding arc will also double. So, therefore, here is a little table. If the arc length, let us say the arc length is 1 unit, then the angle subtended at the center is 1 radian, or vice versa. If you increase the angle subtended at the center to 2 radians, and as we saw on the previous slide, the length of the arc will double from 1 unit to 2 units. If the angle subtended at the center is, for example, any fractional or decimal number, any real number like 3.17 radians, then the arc length will be 3.17 units. Now, we know that for a circle here of let us say radius 1 unit, if I start from this point A, so look at this OA, and I make a complete revolution, which is that I go like this and then come back to A. If you make a complete revolution, then the arc length will be equal to 2 times pi units, and therefore, going by this fact that the arc length and the angle subtended are equal, what I mean is that if the arc length is 1 unit, then the angle subtended at the center is 1 radian, and if you double it, then the angle subtended at the center also doubles. Then by going by that, if the arc length increases from 1 unit to 2 pi units, then it should be clear that the angle subtended at the center by this complete revolution should be equal to 2 pi radians, and therefore, this shows that one complete revolution is equal to 2 pi radians. So, this is something to be remembered, that one complete revolution is equal to 2 pi radians. Here of course, pi, as all of you know, is a constant, it is a universal constant, and it is equal to the ratio of the circumference of a circle divided by the diameter of the circle. So, you take any circle, however small or however big in this universe, if for that same circle, if you calculate the circumference, you find out the diameter of that same circle, and if you divide the circumference by the diameter, no matter how big or small or whichever circle you draw, the ratio is always a constant, and that constant is called pi. Another related question that might come to mind is, so this, let us say that this inner circle here, so I have what, as you see in this figure, there are two concentric circles. So, one is this circle with the smaller radius, and the other one, the outer circle, has a bigger radius, and both of them have the same center at this point O. And let us say that we have a ray here, so this particular ray, and we rotate it in the anti-clockwise direction by 1 radians. So, that the ray now comes here. Then for the inner circle whose radius is 1 unit, we know that the length of this arc will also be equal to the radius, which is 1 unit, right. But let us say that this outer circle has a radius of r units. So, this is what I am talking about, and it also rotates, we rotate this particular ray by 1 radian, and we want to see the length of the arc on the outer circle, which is this length x. Of course, that will not be 1 unit, because 1 unit was the length of the arc in the inner circle, and as you can see, it appears that this is definitely more than 1 unit, but how much is it? So, if you see in this table, for the outer circle, let us say that we do not know this arc length. So, for the outer circle, if this arc length is equal to x units, then as we have drawn it here, the angle subtended at the center is 1 radian. Okay. And from the previous slide, we know that one complete revolution is equal to how many radians? One complete revolution is equal to 2 pi radians, right. So, this is one complete revolution. So, if the angle subtended by an arc at the center is 2 pi radians, that corresponds to 1 revolution. So, if you increase the angle subtended by the arc from 1 radian to 2 pi radians, which is one complete revolution, then the arc length should also increase in the same ratio, which is that if, since here you are increasing the angle by 2 pi times, the arc length should increase from x to 2 pi x. It should increase from x to 2 pi x. But then we know that the arc length for a full complete revolution is nothing but the circumference of the outer circle, which is actually 2 times pi times r, and that should be equal to 2 times pi times x, because that is what we got from this table, and therefore, this x should be nothing but equal to r units. So, therefore, what we see is that we could also define 1 radian very generally as, instead of just looking at a circle of unit radius, in general if we have a circle of radius r, and if we rotate, let us say this, let us look at this radius here on the outer circle, radius is r. Let us look at this radius, this ray. Now, if we rotate it by 1 radian, we reach here. So, in that case, because we rotate it by 1 radian, this particular arc length will be equal to the radius itself, which is r. So, essentially 1 radian could be defined as the rotation angle such that the length of the arc corresponding to that rotation angle is equal to the radius of the circle. The next step is, so this is what we were discussing in the previous slide, that if you have a circle of radius r and you look at this ray O A, if you rotate it by 1 radians, then the length of this arc here will be equal to the radius, which is r units. Next question is, suppose we have a ray OC and I rotate it by theta radians, then what is the general formula for the length of this arc CD? So, again we have a table here. We know that from the previous slide that if in this circle of radius r, if the angle of rotation is 1 radian, then the arc length will be r units equal to the radius. If it is 2 radians, then of course, the arc length will also double, it will become 2 r units. In general, if it is any real number times 1 radian, for example, 3.98 radians, then the arc length will also increase proportionately to 3.98 r. And therefore, if the angle is in general some theta radians, for example, like this here, then the arc length should also increase, because if so, what is happening is that compared to 1 radian, we are increasing it or decreasing it to theta radians. So, there is a multiplying factor of theta here going from 1 to theta, and therefore, the arc length should also increase proportionately from r to theta r, and therefore, that is how we get our answer, that the length of this arc corresponding to this angle of rotation theta will be equal to theta times r units. As many of you would have guessed by now that there is a relation between these measures, which is what we will discuss now. So, we earlier said that one complete revolution is 360 degrees, that is when we were defining what a degree is, and later on we also said that one complete revolution is equal to 2 pi radians, and therefore, since they have to be the same, 2 pi radians should be equal to 360 degrees, and therefore, 1 radian should be equal to 360 divided by 2 pi degrees. So, if you use the approximation that pi is equal to 22 by 7, which is an approximation, then you just get 360 divided by 44 by 7, which is approximately 57.27 degrees. So, this formula here 1 radian equal to 360 by 2 pi degrees will give you a conversion from radians to degrees. So, for example, if I ask you how much is pi by 4 radians is equal to how many degrees? So, it is very simple. Since 1 radian is 360 by 2 pi, pi by 4 radians will be pi by 4 times 360 upon 2 pi degrees, which is going to be equal to 45 degrees. So, that is how you convert from radians to degrees. And then of course, somebody can ask you, okay, if I give you an angle in terms of degrees, how would you convert it into radians? So, that is also very simple again. So, we just invert the whole argument and say that now 360 degrees is equal to 2 pi radians, and therefore, 1 degree has to be equal to 2 pi upon 360 radians. And suppose if somebody asks you to, let us say, find out how many radians is 135 degrees. It is very simple, because if since 1 degree is 2 pi by 360 radians, 135 degrees will be equal to 135 multiplied by 2 pi upon 360 radians, which will be equal to 3 pi upon, so 3 pi divided by 4 radians. So, the conversion is very simple. Let us take a little example here. So, what I have drawn here is a clock. So, as you can see 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock, and it is said that the minute hand of the clock is of length equal to 5 centimeter, has a length equal to 5 centimeter. Now, how much does the tip move? How much does the tip of the minute hand move in 42 minutes? So, let us assume that the minute hand was at this position to start with, and then it has to rotate by some angle, and then finally, after 42 minutes it would reach here. So, let us first try to find out this angle of rotation. Now, we know that one complete revolution is equal to 2 pi radians, but then this is not one complete revolution, right. This is only, so since in this case one complete revolution of the minute hand of the watch is going to be 1 hour, which is actually equal to 60 minutes, whereas we know that in this problem we are asked to find out how much the tip has moved in 42 minutes, and because 42 is less than 60, it is not a complete revolution. In fact, it is equal to 42 upon 60 of 1 revolution. Now, since one complete revolution corresponds to a rotation of 2 pi radians, 42 by 60 of 1 revolution will correspond to 42 upon 60 times 2 pi radians, which is equal to 1.4 pi radians. And then how do we find the length of this arc here? Because the question is asking you how far does the tip of the minute hand move in 42 minutes. So, to find the length of this major arc corresponding to this rotation by angle theta, as we saw on the previous slide, the length of this arc will be L equal to the angle of rotation theta times the radius of this circle. In this case, the radius of the circle is nothing but equal to the length of this minute hand, which is 5 centimeter. So, the answer is equal to 1.4 pi times 5 centimeter, and if you use pi equal to 22 by 7 as an approximation, then you will get it to 1.4 times 22 by 7 times 5 centimeter, which is going to be equal to 22 centimeter. So, this was quite a bit of background which many of you would be knowing. Now, the purpose of this session and the other sessions to come would be to generalize these trigonometric ratios that you would have already learnt in your previous classes to trigonometric functions. So, we go back to sine and cosine again and try to generalize them to sine and cosine functions. So, in this slide what we have here is a unit circle, it has radius 1 unit, whose center is at this point O. This, I call this horizontal axis as the x axis and the vertical as the y axis. Now, consider this point P on the unit circle here, whose x and y coordinates are a and b respectively. So, what this means is that if you project this point onto the x axis, then this length is equal to a units this is A units, and this length is the projection of this point onto the y axis, and of course, that will be equal to B units. And let us connect this point O to this point P. So, if we see this, so what we have here is a right angle triangle, and let us call this angle as x. And now, we are ready to formally define these functions sin of x and cos of x. So, sin of x will be equal to, as you have already studied earlier, if you look at this triangle O P and let us call this point as B, sin of x is equal to B divided by the length of the hypotenuse, but since it is a unit circle, this hypotenuse is of unit length. So, sin of x is simply equal to the y coordinate of this point P, and similarly cosine of x will be equal to A by the hypotenuse, which is again of unit length. So, it is simply A. So, cosine of x is simply equal to the x coordinate of this point, which is A. Of course, now that we are defining these two functions sine and cosine, we need to define the range and domain of this function. If you see this x is real valued, it can take any real value, and therefore, the domain of this function, both these functions cos and sine, is the set of real numbers R. So, the domain is equal to the set of real numbers R, and let us talk about the range now. If you see, for example, for the sine function, sine of x for this x for any x is equal to the y coordinate of this point P. Now, as this point P moves, so if we start with, let us say, suppose if we initially say that P was here, then when P is here, x is equal to 0, and then as you move, let us say, in the anti-clockwise direction on this circle, x starts to increase, and you can keep on going like this. So, as you go, you will get different values of x, and for each value of x, you can actually measure the x and y coordinate, because for each different x, what you have is a point on the circle, on the unit circle, and you can, from there you can find the x and y coordinate, and therefore, you can actually find sine and cos of any x like that. But one thing to be seen is that this value of b and value of a for any point P on the circle has to be less than 1. The reason being that this point is on the circle, and it's, and therefore, since the radius is equal to 1 unit, and both this a and b has to be less than 1 unit, because if you see this right angle triangle here. So, for example, if you see this particular point P, so this a is obviously less than, and similarly this b has to be less than this radius here. If you project it here, then this is equal to b. So, that also has to be less than the radius, and the radius is 1 unit. So, one thing is for sure is that both have to be less than 1, they can be equal to 1 also. Now, for example, let us say that this point P, so this is an upper bound. So, a always has to be less than 1, because the largest x coordinate of any point on this circle will not exceed this point. So, the coordinate of this point here is 1, 0. So, the x coordinate of any point on the circle cannot be more than 1. So, that is why a is less than 1. Similarly, the y coordinate of any point on the circle cannot be, because this point is 0 1. So, no y coordinate can be above or above this particular line, let us say. So, we have this line here. So, no y coordinate or no point will be above this line. So, therefore, b has to be less than or equal to 1. On the other side, for example, if we the moment we rotate it more than 90 degrees. So, let us say we have a point here q. So, obviously, as you can see, the x coordinate of this point is negative, and the largest negative value that the x coordinate of any point on this circle can be is when we reach, let us say we rotate and reach this particular point whose coordinate is minus 1 comma 0. So, the x coordinate of any point has to be greater than or equal to minus 1. Similarly, the y coordinate also has to be greater than or equal to minus 1. So, as you can see, the range of both this sine and cosine functions. So, this is the range of both the cos, because sin x is b and cos x is a. So, the range of both the sine and cosine function is between minus 1 to plus 1. So, there are some other properties that given that we have defined these functions, we can discuss some properties that these functions will satisfy. So, if we go back to the previous slide where we had drawn the circle, let me draw a circle for you right now. So, this was the x coordinate, x axis, and this is the y axis here, and we had drawn this point P with x and y coordinates as a and b respectively. So, this was x, so this was a, and this length was b. This is O. Let us say that this point here is a, and we had said that sine of x is equal to b and cos of x is equal to a. Now, if you look at this right angle triangle over here OAP, then from the Pythagoras theorem we know that OA square. So, OA is the length of this segment OA, OA square plus AP square is equal to OP square, and therefore, this now this OA is nothing but A. So, essentially what we are saying is that A square plus B square is equal to OP square. Now, since this is a unit circle, this OP is equal to 1. So, this is equal to 1, and A is nothing but cos x. So, what we get is cos square x plus B is sin x, sin square x equals 1. So, for any x, sin square x plus cos square x is always 1. Now, we said that sin x and cos x will lie between minus 1 and plus 1. So, when does it happen that sin x becomes 0? If you again look at this circle here with points on the circle, sin x is equal to the y coordinate of the points on this circle, x being the angle of rotation. So, sin x equal to 0 basically means that we want to find out for which point does it happen that the y coordinate becomes equal to 0. So, that of course, if you look at this circle and all the points on the circle, there are only 2 points where the y coordinate is 0. So, one is this point here, which is 1 0. Now, for this point the angle x is equal to 0. So, this is one solution, that sin x is 0 when x equal to 0. The other point where the y coordinate is 0 is this point, and you reach this point from this point by rotating this ray or this radius by pi radians or 180 degrees, which is essentially half a revolution. So, for sure we see that sin x equal to 0 when either x equal to 0 or x equal to pi, but then we must also realize one thing, that both these functions sin x and cos x, their value will repeat if we increase or decrease x by multiples of 2 pi, because 2 pi radians corresponds to one complete revolution. So, for example, suppose we consider this point P, where for which sin x is equal to the y coordinate. Now, if we rotate this starting from OP, if we move it in this direction and make one complete rotation. So, instead of this x, what the angle that we are going to have is, we are going to do something like this. So, one complete rotation and then another x. So, the angle that we are looking now is not x, but x plus 2 pi radians, right. But what we realize is that the coordinates of the point correspond, because after x plus 2 pi radians also we reach the same point P. So, therefore, it can be concluded that, and since we reach the same point, the x and y coordinates are definitely going to be the same, and therefore, we can conclude that sin of x and sin of x plus 2 pi are the same, and the same thing will happen if we see x plus 4 pi or x plus 6 pi, because adding 2 pi radians is just going one complete revolution, and that is not, when you go one complete revolution, you do not change, we basically come at the same point on the circle. So, we can write that in general sin of x is equal to sin of x plus k times 2 pi radians for any integer k, and the same thing is true for cosine also. Cosine of x is equal to cosine of x plus 2 pi, and that is also equal to cosine of x plus 4 pi, and therefore, cosine of x is also equal to cosine of x plus k times 2 pi for any integer k. And therefore, now going back to this problem where we started from, which was to find out those values of x for which sin x is equal to 0. In addition to x equal to 0 and x equal to pi, there will be lot many other solutions, because since x equal to 0 is a solution, x equal to 0 plus 2 pi will also be a solution, and therefore, 4 pi will also be a solution to this equation sin x equal to 0, and therefore, from that we can conclude that sin x will be 0 equal to 0 implies and is implied by x being equal to an integer multiple of pi. So, you take any integer multiple of pi, if you take the sine of that angle, you will get sin x equal to 0. So, k could be any integer. So, it could be negative also. So, in this class what we studied was a little bit of background of what all you had studied in your grade 10, and we then tried to generalize the basic trigonometric ratios to two trigonometric functions, sin of x and cos of x, and we discussed some basic properties of these two functions. In the next class, we are going to continue with some more properties of these two functions, and later on further discuss more functions like tan of x and other functions. Thank you.